buffer a little bit. All right, just letting this buffer to get started here. Okay, so now let me do this. Oh, where's my Zoom? Share screen. I think I want screen 1. Whoops. And then I just need to move this over here. All right, so this is the Canvas website. Just wanted to mention something before we get going. In particular, I was telling the class, I rarely do anything extra credit. My opinion is the way to get extra credit is get extra of the regular credit by studying. I know that sounds crazy, but let's take a look here. Extra office hours. This is in Canvas, so you know where to get it. I just want to point out, I believe this is tomorrow, right? Tuesday, 2/8. I don't know if you can see that. Let me make it a little bit bigger. Sorry, it's a little bit crazy. So tomorrow, I'm going to move my Zoom office hour, but I'll be in the Mesa Center. So basically, look at this. I'm going to take your lowest midterm and add 5% extra credit. Why am I doing this? Ever since COVID, people have gotten out of the habit of meeting and collaborating in person. I know there's risks, and depending on your situation, all right? So maybe this doesn't work out for you, but what I'm trying to do is encourage real face-to-face interaction, including seeing the people that are already done with this class in the Mesa Center. I'm trying to encourage this thing that we used to have here on campus, where basically the people who had already suffered through me could help out the people who were currently suffering through me. Don, do you have anything you want to say about that? Or like the vision of why we're doing that, or is that close enough? Working alone is miserable and inefficient. So if you learn how to work together, and maybe basically I'm giving you this opportunity to see this place and get extra credit on the test. That's a ridiculous amount of extra credit for showing up. The other thing, think about this. It's also, look at this, there's one this Saturday too, which I'm not looking forward to, but I'm going to be there, right? So think about this. You have to give your first talk. You are all pretty bad at giving scientific talks because you haven't given a lot of it. There's 10 extra office hours this week. You can come in and just say, look at my talk. Can you critique it? I'll help you. Or you can say, I did not understand this step in the solutions on problem 2.86. Geez, I hope there's not an 86 in there, but there might be. Anyways, everybody aware of the opportunity on Zoom as well? Sweet. This is our last day of chapter 2 in the workbook. So I'm going to kill this. Don't think we need this. Okay, so that's just letting you know of that opportunity. You know where it is. And if you can't make it this week because that's too short of notice, I think it was in week 5, which is close to the exam week. There's going to be another 10. So there's 4 opportunities to make that. 1 Tuesday, 2 Saturdays, and 1 Friday. Look it up, put it in your list of things to do, and make it. Okay. Yo, I'm listening.
I got a gyroscope.
You got a gyroscope?
Yes.
Sweet. What chapter is that today?
Angular momentum.
Yeah, so that's 11. Sweet. Yeah, let's look at it on the break, eh? That's pretty cool. I want to check it out. I just got to get rolling. Make sure I got some markers, and then we'll get this. So on Zoom, I'm just doing a quick marker check. Just give me a sec.
You learn it.
What's funny is that I don't remember saying that, but it sounds like something I would say. What did you do there?
All right, let's focus. Here we go. Okay. Come on. Come on, Zoom. Come on, Kim. There we go. All right, and then I can get rid of this because I don't need that right now. So now I'm on the screen. All right, so my goals for today are twofold. We want to talk about multi-stage 1D motion word problem. Okay. Now, one of the big things with these types of problems, you can argue that they're somewhat artificial and contrived, and I would agree with you. But one of the things that a lot of students are bad at is writing down systems of equations from physics words, right? So you see these words in a problem, and some of them have certain special meanings that are supposed to trigger thoughts in your mind. Like, for example, you have a cop chasing a speeder, and you say, when will they reach the maximum distance of separation? That's a term that has an implied equation associated with it in physics, and there's several others. So we're going to try and go through those. At the end of today, we're going to try and learn about separation of variables. So up until now, we've been dealing with constant acceleration. This is one technique to deal with non-constant acceleration in calculus. Right? So that's our two goals for today. Right? So let's start. I'm going to pick one over here. I think I have one that I like. Give me a second here. Let's look at page 26, problem 2.6. Okay, those are our two goals for today. Okay. Now, let's do a multi-stage example. Problem 2.6, page, what did I say, 26? Huh, that's kind of cool. Okay, so a driver is driving with constant speed. We see a bunch of words here. Does anybody remember what the first thing that we might want to do in the problem-solving strategy was? Draw a picture. They don't have to be good. Here's a driver. Great, it's a car. We're told this driver is traveling with some speed v, is that right? On a straight road. Okay, the driver sees a deer some distance d away. So here's my deer. Kind of looks like a spider looking thing. It's a mega deer. It's much bigger than the car. So what? And we're told it was distance d away. Okay. D away. After taking time t subscript r to react, the driver applies the brakes, which causes the car to slow down at constant rate. Okay. So somehow we have to label this reaction time. I'm going to write this sentence first, because this is the key bit. Okay. Now, in this case, maybe we could try and put this in there somehow with some kind of line or something, just some sort of visual, right? So I'm going to choose to do it this way. Now, wait a minute. Does this person hit the deer or not? I'm going to read the questions. What minimum rate of slowing will cause the car to stop before hitting the deer? While the car approaches, assume the deer remains in place like a deer in the headlights. All right. So I think this is reasonable. We're supposed to just barely miss the deer, right? Okay. So if the car stops right there, they won't hit the deer. All right. What does slows at constant rate imply? Yeah. Constant excel opposite direction of V. All right. Now, in this case, what about this stage? Is this this stage over here where they're reacting? Is that constant acceleration?
Yes, because it's moving at a constant speed.
I heard a yes. What? Speak up. I just get the mass and all the blowing fans.
It's moving at a constant speed, so it reacts and slows down.
Yeah. So what is the acceleration over here? Yeah, here the acceleration is equal to 0. So here what we're doing is we're taking a problem that doesn't have constant acceleration and splitting it into two problems that are each constant acceleration separately. So far, so good? That's the key tenet of this state. So both problems that we're doing today, both of our goals today, are different ways of handling non-constant acceleration. One way is to split things into multiple stages and do separate word problems just like before with our variables, and we're going to do that in just a second. The other way is to try and use calculus. All right, that's what this day is all about. Handling problems where the acceleration is not constant by splitting into stages. We're doing calculus. All right, so now what we might want to do, I'm going to do this. I'm going to go over the other board, right? What I like to do, at least when I'm starting, is split my paper in half vertically. Normally, I don't work in columns. But if you have a big picture like the one we just drew, right, we could have one for stage 1 information. And this was constant speed as driver reacts. Number 2, that was stage 2. It's not only an album from Boston. Oh my gosh. Nobody's got that name. All right. We have the driver slowing at constant rate and comes to rest before hitting deer. All right. So these are our 2 stages. So far, so good? Let's take a look at the equations we could write. Now, I'm going to choose to put a subscript on here. You don't have to, but you don't have to get the problem right, right? You don't have to be organized to get this problem right. It just makes it more likely to get it right. So subscripts are going to be our friend. And I don't care about the order of the subscripts either. Let's do it this way. Okay. The idea is anything with stage 1, I'm going to put a subscript of 1 on it. That way I can keep track of it. Now, if you have multiple colors as well, I don't think it hurts to use multiple colors, right? So you don't have to though. And the idea is then it makes it very obvious which stage I'm talking about when I use a variable. I'll get out of the way. Okay. All right. So in this case, do I know anything in either of these charts? Let's go through stage 1. Do I know how far the driver travels in stage one, like right off the top of your head? No. Okay. How about V1 initial? Do I know that? V. That was the label chosen for us. What else did we say about the acceleration in stage one? 0. What does that tell us about the final speed in stage, the final velocity in stage one? It's also V. If you have no acceleration, no change in V, right? It doesn't mean no V, it means no change in V. Do I know the time for stage one?
TR.
TR, okay. So again, we're just taking the variables from the problem and associating them with the variables in our standard constant acceleration kinematics. So I'm going to put this here. All right, in this case, let's move over to stage 2 before we get ahead of ourselves. Do we know how far it travels in stage 2? No. We know that the total between both stages is d, but we don't know, right? This is not d, this is the change in position for stage 2. If I could, give me a sec. Oops. This distance is d. This distance is change for stage 1. This distance is change for stage 2. So that it's not d. Do you agree? It should be less than d. And that's something we could use to check our answer at the end. Good. All right. So I'm going to just put in that we don't know what it is. We know it's got to be related to d somehow, but we just don't know exactly how yet. Agreed? Do I know V2 initial? How do you know that? Just kind of explain in words. I know it seems kind of obvious, but just say it anyway. What gives you that clue that this should also be V?
Because
Go ahead.
it starts off with where the previous B.
Yeah, that's kind of what I wanted to go for. We know that the initial of stage 2 should equal the final of stage 1. Agreed? And that's all. And so if that wasn't obvious, I apologize if I did a bad job explaining that. We know that final of stage 1 is, and I'll say V final. Does that make sense? That's always true, whether it's some other problem, right? When you split problems up into stages, the final from the first stage is always the initial for the second stage. So that tells me this is V. Do I know what V2 final is?
0.
Why?
Because it comes to stop.
And we can see that the trick in doing these problems is reading carefully, making sure you can tell which set of words gives us some of these knowns, right? And once you see that we can get some of these knowns, then we're halfway there, right? The equations hopefully will work themselves out. What's the acceleration? Do we know it or not?
No.
Is that what we're looking for? Or not? What are we trying to find?
What kind of rate of slow?
Rate of slowing.
It's the acceleration.
That's what we're looking for, right? Time 2, do I know it? No? Okay. Okay, and so here's the crux of the problem. Look, there's 4 things we don't know here. Now, I suspect we can probably figure out this one pretty easily with an equation. But the trick is, usually with a 2-stage problem, there's some sort of connection. Sometimes I like to call that a constraint. There's something in this problem that's constraining the 2 parts together, right? Or maybe we could just call it a connection, all right? Does anybody see any connections between the variables over here and over here that we haven't listed yet?
Time.
What about the time?
Shouldn't it be T2 BTR?
No. Do you agree you could take, like, say, half a second to react and 10 seconds to break? So we don't expect this time to be the same as that time. What do you think?
The distance.
The distance, what about the distance?
So
change of x cubed equal to b minus.
I like to write it as a plus, just because it'll make more sense, but yes. You're saying change in x2 is equal to what?
B minus change of x1.
Sure. Now, what I was saying is I might like to write this as this. The sum of the two displacements in this particular problem should equal D. Do you agree that's the same sentence?
Yeah.
So here's where one person might view it one way, another person might view it another way, but the idea is there's some sort of connection between these distances. Why is this useful? Let's think big picture now. At some point, we're going to use some kinematics equations of constant acceleration motion. I could probably learn about delta x1. Once I learn about delta x1, I can use algebra to get delta x2, and then I only have two things I don't know. It should be a solvable problem. So far, so good? Now with this one, you might be saying, dude, this is too easy. I know from experience, I can just figure this out in my head. That's true. You might be able to do that. But you can't do that with every problem. I like to say this, let the paper do the work. Put stuff on paper and write it out. You might be saying, oh, I'm going to waste too much paper. No, you will be faster at doing problems if you get the information on a piece of paper so you can see it and communicate and show others and things like that. Yes, this particular one, maybe you are the kind of student that could do this in your head. Most of us are not. And the next problem and the next problem get harder and harder. Enough said on that? I don't know. Yes, questions?
So for the distance one, so that means that the car would come to a rest by the time it reaches like the end of D, right?
Say again, the car would come to rest just before hitting the deer, which is basically at distance D.
So it takes up the entire distance.
Yeah.
The entire D. So it's not
That's
just
right.
like, it wouldn't slow down before like finishing power.
Well, so it's going to drive at constant speed for a little bit while the driver reacts, and then it will start braking, right? And so what we've done is we've taken this problem where it's not constant acceleration, it was 0 then negative something, right? And we expect this thing to I don't know, is that good?
Yeah, I was just wondering, what if it slowed down before it even reaches the D? Like,
Oh, well,
in that case, you can't really say that.
you're right, but what did the question ask for specifically? Look carefully at the wording of the question.
Be like before.
It asked for the minimum rate of slowing. Do you agree?
Yeah.
So, right, do you agree? There's many, what he's saying is there's many other correct answers. I could break a lot harder than this, but we're not looking for all correct answers. We're looking for the slowest possible rate, right? Just so the bumper kisses the deer and says, hello, welcome to Illinois. This happened all the time out in Illinois, right? People would hit deer and they go through the windshield and stuff. I don't know, probably out in rural areas here it happens too. Serious danger, right? All right. Good on that?
Yeah.
It's that word minimum that clues us in. So notice yet again, the phrasing of the problem is crucial. All right, let's do this. I happen to know when acceleration is 0, there's only one useful equation. What's the equation that you first come to mind when we're thinking about constant acceleration kinematics? Give it to me. Give me any equation. Is it okay if I use delta x? Delta x1 is equal to?
BT.
Yeah, I'll say 1/2 a sub x t, and let's put ones on there. Right? And since in this case, a is 0, you get delta x equals bt. Well, wait, don't we know all this crap? That's just b times tr. Oops. You agree? So we know delta x1. So now I could take this and plug it in here. When I do that, what is delta x2 equal to? Somebody. Just give me the equation. Don't overthink it.
D minus BTR.
Yeah. So it's not just one letter anymore. You can see we're building up the complexity. All right, so we've got that. All right, let's look. What kinematics equation is going to get the job done? we've got the delta x equation. And again, remember, I don't care much about the order of the subscripts here, right? When I have v initial x2, that's v initial, right? That's always velocity initial, horizontal direction, stage 2. You could have said v2 initial x, same thing. I apologize if that annoys you. But basically, all of these subscripts have a meaning, so if you just have all of them in there, it makes sense to me. All right. So let's keep going. There's also again, just trying to get this fluid here. Whoops. And notice, I should be careful here. Wait, what did I forget here? Yeah, T2 squared. Notice I'm trying to be good about my subscripts. Notice everything in stage 2 has a subscript 2 on it. You don't have to do that, but like I said, if you're not organized, what if a problem has 3 stages or 4? It just rapidly gets unwieldy. It's like in code, right? If you're going to have multiple stages in code, you might want to have different labels for them, right? You don't want to use the same label for everything. It's just bad practice. What's the last kinematics equation? Is it the squared one, I guess? These are the big, there's others, but whatever. Is that still on Zoom screen? Okay, thanks. My screen just went black. They're going to check that out for me, but so it's like every 5 minutes the screen turns off, so I have to kind of. Okay. Now, here's a tip. Before we start plugging in crap, we could check which things are going to give us results. In the first equation, do I know delta x2 at this point?
Yes.
Yes, this is delta x2. Do you agree d is a known, v is a known, and t sub r, those are all knowns. So I actually know delta x2. Do I know a sub x2? No, that's WTF. Do I know T2? This is not looking good. This I know, but that's a lot of question marks. Let's go to the next one. V2 final, known. V2 initial is known. Unknown, unknown. Okay. Here, known, known, unknown. Aha. So I argue by doing this quick check, what's known and unknown, sometimes this can save you some effort. Everybody cool with that? All right, so let's plug in our knowns. This is 0. This is equal to v squared when we plug it in. And just this was, what was it? D minus v tr. Jules, am I still on Zoom or did I creep off the edge? Okay. I'll zoom out just a little bit, just in case, to give us a little bit of wiggle room. Thanks, Jules. Appreciate it. All right. Do you agree this will get us the answer that we want? Okay, so just because I'm on Zoom and I'm running out of board space, what I'd like to do, actually, I think I could just do this. Let me see if I could do this. Whoops, wrong way. Okay, we're just working with this now. I can basically go all the way to this thing. All right, so let's rewrite this equation up here so we got something to work with. All right. So for me, what I would do is I would probably move this v squared to the other side, right? So that's going to be, I'm going to subtract v squared from each side. And I'll get negative v squared all right. Heads up. Listen, Is this squared? Cancel that minus sign. No. Okay, I just want to point this out and stress it. I apologize if this is obvious to you, but think about this. If you plugged in a number here for b, right? If this was -3 or whatever, -3 squared would become 9. Then you'd be subtracting 9 from each side. You better get -9 over here. So to be clear, what I'm emphasizing here, negative v squared is the same thing as negative of v squared. So you do the squared first, then do the negative. This is standard way of writing it. It is not equal to negative v squared. Right? Negative v squared is not negative v squared. You got it? Just being clear. Man, that looks like trouble, doesn't it? Well, let's finish solving this for a. We get negative v. Oh, I don't like that color code there. Let's go back to black. All right. If I solve this for a sub 2x, I need to divide by this and this crap. So I get negative v squared divided by 2 d minus vtr. You buy that? Take a second to do it yourself real quick. All right. We got a result. What should you do when you get a result? What's something you could do? Check the units would be a good thing. Also, check what else?
What you're looking for.
Okay. This is what we're looking for. Yeah, the sign. Does the sign make sense?
Yes,
Why?
because it's in the opposite direction. of the velocity.
Yeah. Our velocity was positive here. And so we expected, somewhere we wrote this down, I don't remember where, but we said we expected this to be opposite the sign of this. Well, if this is positive, we expect a negative number.
So we're there.
Okay, cool, thanks. All right, let's check those units. Checking the, so the sign looks good. Because we said slowing implies A is opposite sine of V. That looks good. And checking the units. What are the units on top? What are the units of the minus sign? None. What are the units of V squared?
Here square over second square.
Okay. What are the units of 2? Nothing. That's just a constant from calculus. Okay, now here, what are the units? Yeah. Okay, this one's meters minus. Now, the seconds drop. What are the units of meters minus meters? Meters, right? 3 apples minus 2 apples is 1 apple. Still the same units. So what do we get for our final unit check? Meters per second squared. Looks good. It's an acceleration. Units check. Agreed? What's another way we could check this result? You know me, I like to bring up a good weed reference. If you were stoned and you were driving, what should happen to your reaction time?
Slow down.
Slows down. So what should happen to how hard you have to brake?
Speed up.
You would have to brake harder. You expect the value for A should become a bigger negative number if you're drunk or stoned, right? So in this case, if T sub R gets bigger, what happens to the denominator in the basement? You have D minus a little bit bigger number. What happens to the denominator? It gets smaller, so what happens to A? Got it? This is the power of algebraic. Not only can we check the units, right? Not only can we think about the signs, sure, you can do that with numbers too, but now we can play around with this in our mind and think about what if types of questions. Obviously, if the reaction time was too big, you just hit the dude. So far, so good on that? Question.
So like if they're both on the numerator, proportional, right? If one is in the numerator and one is in the denominator, they're inversely proportional.
Yes, yes. So we would say A is proportional to B squared. A is inversely proportional to D minus VTR. Good? Yeah, good question. Yeah, this last step, right, you might not want to do it all the time, but what will happen is over time you can see the merits of this. Imagine you're employed and you want to take something to your boss and you want to make sure it looks good, right? Checking the units is not sufficient. You want to make sure it behaves correctly, right? Because your boss is going to do this in their head the second they get there. They'll be like, wait a minute, right? If TR goes up, oh yeah, this looks good. If TR goes up, that means they're slow, right? They're going to think through that as well. So your boss is going to expect you to do some of these simple calculations as well to kind of check some cases. All right, what do you think? Ready to try one on your own? All right, let's try this one here. Let's go to page. Where was that? Give me a second. Go to page 41. Give me a sec here. Okay. Okay. So I know there's a couple of heads here. We've got, I think it's basically you two. Your heads are just kind of slink down low. Be cool for a minute, you know? All right. So it's okay. Or if you want to just walk to the side just so the Zoomers can see, that'd be cool too. All right. So I've got two cars here. All right. This is called a constant speed card. And let's make sure it's cranked. All right. So the idea is when I turn this thing on, hopefully it's pointing the right way. I think I got to point it this way. There's a DC motor in here. And when I turn this on, it's going to go at constant speed. Agreed? Doesn't look like it's accelerating too much. It's going by eye. Right? Now, if you care, and let me see if that's, oh, perfect. Thanks, guys. I appreciate that. Right? So, and all of you in class, I appreciate this, and all of you on Zoom dealing with the whole headache of this and that. So that's pretty cool. So now over here, I've got this fan card. Now what I'm going to do is turn this on. Give me a sec. I'm going to crank it up to high speed. I'm going to set it to a 6-second pulse. All right. And the idea is what we could do is we could have a race. Give me a second. 1, 2, 3, go. That one accelerates. Good. It still didn't break. Looks like a 4-second pulse will do it. All right. You want to just come around and catch it for me? That'd be cool. All right. So in this case, we're going to have one car that moves with constant speed and another car that moves with constant acceleration, right? And so when I run this one, let's just kind of get an idea for this. Zoomers, can you see this at all? Is it kind of, okay, thanks. So what I need to do is think, I got to hit this and then turn this on. So I got 1, 2, 3. Okay, whoa. All right, let's try that one more time. Let's make this a little bit more dramatic. This one's accelerating so fast it catches it almost immediately. So let's go to medium speed here. Let's try that again. All right, so we'll do 1, 2, 3. Okay, it's not perfect. All right, so this is the idea. All right, thank you. Let's give him a round of applause here. Very good. And we can do this again later at the low speed if we need to. But I want you to look at problem 2.36 on page 41 while I get the board erased. The concept in 2.36 is exactly the same as this. One car is driving at constant speed. One car is accelerating. The cop is the accelerator and is going to catch the snail. Give me a second while I erase the board, okay? You keep read and start it if you want. There we go.
I'm sorry. I don't know what it is, but I heard something. Well, that's my birthday.
Famous physics problem. A lot of you probably did this in high school. Again, you can start that problem if you're waiting for me. If you've done it and it's too easy, just do the whole page. Still erasing if you're on Zoom here. Almost there. What's the first stage in attacking this problem? What should you do, probably? Draw pictures, all right? This was probably what, 2.36? Okay. So it's not exactly the same as the last problem, but it's similar. The cop is sitting here at rest. Man, look at that S car go. Snail joke. All right, I tried. You like that one, Don?
It's an old one.
An oldie but a goodie. Okay, don't make me get out my cross product jokes. Okay, so here we go. What I would do here is, instead of having stage 1 and stage 2, I would have one problem for the cop and one problem for the speeder. Now, you may not want to use the symbols S and C. So maybe you could call the speeder number 1 and the cop number 2, right? And then what we could do is we could split up our page. We could have one list here for the cop. They might not have the same time, they might have the same time, I don't know. But the idea is we're trying to make these problems all look similar, where we do a similar procedure. That's the difference in physics versus, say, history. Instead of memorizing some facts, right, we're trying to memorize some procedures, so to speak, right? And it's not exactly that, and I know in history there's qualitative analysis and things like that too. But yeah, whoops. Instead of learning a set of facts, it's more important that you learn these procedures. On your test, you're not going to be able to memorize your way, you're not going to be able to memorize your way through a physics test. You can learn procedures to get through a physics test. Those procedures should carry over into your engineering classes or things you might actually care about. Okay. So you're going to make a list for the number 1 car, a list for the number 2 car. And then, similar to the last problem, sometimes there's some connections. Hello, good English. Put the X in there just for fun, all right? Connections, or sometimes we call those constraints. These are equations that connect the 2 pieces of the problem, right? So this is basically a 2-stage problem. You've got a cop stage and a speeder stage, and there might be some connection between them. The hard part in the last problem was not necessarily listing what's known and unknown, but what was the hardest part, probably? The connection. So let's start there. Okay. Part A. So I'm going to write this here. Part A. Max distance between cop and speeder. What does that tell us? If we're looking for the maximum distance between the cop and the speeder. Okay, we're looking for which delta x? I want the distance between them.
like delta x of speeder minus delta x. of the cop.
Yeah, and I'm gonna do it, okay, so you're right, we're looking for some kind of distance, we're looking for some kind of delta x, and it has to do with the difference between them. Distance between, right, should be, in this case, it should be delta x1 minus delta x2. Remind me, what does delta x mean in these equations? Strictly speaking,
The change in,
change in what?
it's
Change in what?
displacement.
Displacement. Now, I keep saying distance. Why is it okay for this one special problem to exchange the words distance and displacement?
They're going in the right direction.
Because we're only going to the right, everything's positive. So in this case, I know that the absolute values of these should be there. Now, what if we weren't sure which one would be bigger? What could I do if I wasn't sure which one of these two terms is bigger?
Absolute value.
Nice. You could take an absolute value. In this case, we just watched a demonstration, right? The maximum distance occurs when the speeder gets really far ahead and the cop hasn't caught up to speed yet, right? Okay, so this is what we're looking for. There's more information here. I need something else. What else does this tell us? It's okay if you don't know this, and I'm going to tell it to you in a minute if you can't figure it out. When does the maximum distance occur? Yes.
When the cop reaches the same speed as
Yes.
the speeder.
So there's two pieces of information. This is what you're looking for, but this is what you know. It occurs when velocity of the cop equals velocity of the speeder. Now let's walk this through in our brain. If the speeder is going faster than the cop, the speeder is getting farther and farther away. If the cop is going faster than the speeder, the cop starts gaining on the speeder, agreed? So this is what you're supposed to know. When you see these words in a physics question, I expect you to know this. If you don't, memorize that and never forget it for the rest of your life, or at least for the rest of this class. Cool? So this is one of the annoying parts in a physics problem. That's a lot of information in one little sentence. So far, so good? That is the constraint for part A. How about part B? Let's read part B. How far from the origin is the cop when she finally overtakes the speeder? Okay, part B says, how far, hope I'm on the right whiteboard. Yeah, how far from, okay. Okay. How far is the cop from the origin when she overtakes the speeder? What does that tell us for a constraint?
When the velocity of the cop is more than, or not.
We would expect that the velocity of the cop should be more than the speeder, but do you know how much more off the top of your head? Okay, so that's something you could use to check your result, but that doesn't really help us. We do expect the cop should be moving faster than the speeder. So I'll write that down here. We expect the cop should be greater than the speeder, but we don't know by how much. But that's a way to check the answer. That's good.
Oh, with the, and when the cops and the speeders displacement is the same.
Exactly. In this particular problem, we expect this occurs what would be the equation I could write? Say it, yeah, what would I write for the equation?
So x1 equals x2.
Yep, and we call them delta x1, but in this case, do you agree if you start from x initial equals 0, delta x1 and x1 are the same?
Yeah.
And to be clear, these are displacements, but we can call them distances because everything's moving to the right, never reversing direction. But again, we want to be careful. The only time we could use distance instead of displacement is when everything's moving in the same direction and not reversing direction, right? So, okay, at this point, do you feel like you have an idea of how to attack this problem? Yes, no, give me a thumbs up, thumbs down, thumbs sideways. Okay, so what I'd like to do is have a second for you to work on it. We'll all circle. And here's the deal. 2.37 and 2.38 are increasingly harder versions of this problem. One of them is a cop and speeder problem where you add in a reaction time. Or one of them is one where you add in a max speed. And if you could do all three of these, 36, 37, and 38, you could probably handle what I throw at you on test day. Let's take a minute and go, all right? Try getting these, right? It's all about getting these, and these. If you can get these three sets of things, your equation should work out. All right, I'm gonna circle. I see something in the chat there. Is that you, Jules? Oops. Thanks for getting that. Appreciate it. Got it. Okay. So I'm gonna circle. You guys can try and get this going. All right. Nice job, everybody. Nice job. And don't forget, you've got the solutions. If you need a laptop, grab one. Okay. That's my deal.
Yeah.
Okay, bring up the hovercraft for you. So you can spin with the chair stuff last time. Do it in class. Remember the rocket?
Oh, yeah.
Yeah. So it works better when you have a hovercraft. So we'll have that up here today, I think. I'm sure it's that. So. You guys have an idea? Yeah. Yeah, that's a good point. So when they say driving at speed, that somewhat implies a constant speed. That's a good question.
Yeah.
So that's something that you might write down as an assumption, right? If you drive at this speed, that's an implicit assumption that it's constant. That's a good question. Yeah, yeah. One more joy of physics, right? Yeah, we get it. What do you think? How you doing? Good. How about you? How you doing? Great, good. What do you think about you? All right. Try and get that list.
Besides the initial velocity and the acceleration stuff.
Doing all right? Okay, okay. Just finish it, just blast on through the other one, try and get them all done. They get harder. Maybe I'll do this while you guys are here.
Oh, are you sure?
Oh, I have one. Just trying to get a sim running too. Oh, zero. There we go. cruising along. I don't. Anyways? Okay. Okay.
Confused about do your algebraic answers like this.
Oh. Remember that part where I was talking about, oh, what happens if T sub r is longer? What happens? That's what I'm talking about. So, for example, if the comp has a greater acceleration, you might expect the maximum separation might be what, bigger or smaller? Something like that. Does that make sense? So basically, think about what happens physically in the situation if one of the parameters gets bigger or smaller.
Yeah, that's what
Yeah, okay, is that cool?
Yeah.
Yeah, that's it, that's it.
I was wondering if you wanted like some sort of algebraic.
No, I just wanted you to think. That's it, that's it. Is that cool?
Yeah.
All right. What do you think? Get somewhere? We should use
Therefore, delta x2 of the comp is, I think, unknown. We don't know how far the comp's gonna travel, right? Because that's in the, they're both driving it. Remember, this is the part where the faint part is trying to catch up to the speeder. So it's gonna travel somewhere, but we just don't know how far. Is that good? Yeah. Get somewhere. If you're getting stuck or having trouble, open up the solutions. And if the solutions don't make sense, I will help you make sense of them, right? I'm just trying to let people work at their own pace here for a minute. Yeah. Yeah, exactly. So what's the acceleration of the speed? If you're driving at if you're driving at 8 miles an hour, straight on.
Oh, because that's what it tells you, right? Yeah.
0, right? That's what this sentence is like.
For me, I still don't think that the velocity of the comp is the same as the speeder because it's accelerating
Yeah.
and it's gonna
now there's only 2 things.
overtake me like when it catches up,
That's
right?
pretty standard.
That velocity is higher.
Good.
No, I'm talking about for beat.
For me, no, it's greater.
Yeah,
Get
so
somewhere?
then we don't know.
There's actually no.
I just don't know what equation
That's
to
what I'm saying, like
use.
the V comp plus the original.
Yeah.
That's better visualized when you got it, right?
Okay?
Just
Yeah.
how you come out. Economics, you also have to-
Cool. Yeah. So that's the thing is, it's trying to tie, that's why I waited to do this problem until after we went about plotting. Because now, if you wanted to plot these things or sketch them, you could get a feeling for what the plot should look like and relate that to the physical scenario. We've got a simulation I'll show you in a minute. What do you think? Good?
Yeah, I'm trying to figure out the equations.
Okay. Remember, they're on the back of your workbook too, and that's on your test, so you can look at the back of the workbook if you need it. Hey, everybody, let's talk about one other connection. This is not always true, but in this problem, what's true about the 2 times? They're the same. So in this problem, not in every problem, right? In the last problem, there was a reaction time. In this one, they start and end at the same time. You could argue that's also a constraint in this problem. Maybe that helps if some of you didn't see that right away. Okay. So far, so good. Okay. What do you think? Okay, you work.
Yeah.
Stay out of it.
Just
What do you think?
What's up?
Yeah. maybe. So
I was just
now
trying,
I
okay, right now
don't
I was just visualizing the last first time. Now I have to do the position first time.
Right.
Because I thought this was a.
Okay.
I know, for some reason I know it would look something like.
I can't do anything without numbers. This is confusing me.
Wait, do they like
Like
position?
in-
What does the intercept mean?
Intercept means
The intercept,
oh,
the vertical axis intercept.
it means the original. Oh, okay, so they both switch it starting forward.
Yeah.
But once when the
Yes.
constant velocity be the ones increasing.
Yes.
Okay.
Got it? Now, wait a minute. These are not consistent. What is the maximum distance of separation in your picture on the plots? Show me the maximum distance. Where does that occur? Approximately in this plot. Point to it with your pencil. Where's the maximum distance of separation? Approximately.
That,
Somewhere in there where the
Yeah.
gap is the biggest, right?
yes.
Isn't that right there? Shouldn't this gap line up with that crossing?
Oh,
You see what I'm saying?
yes.
Yeah, yeah, and that gives us a more physical, so try making a parabola a little more like this, and this a little bit more down, and now we have room to get it. And you know, right here. Oh, and then how far should this go? Right?
Because at this
If we're
point,
going to the point where the cop overtakes the speeder, how far up should that line go?
displacement. Oh, when they both reach the same space.
So
So
when are
I
they
would
gonna have
have
the most, when is it gonna have the most? the same
when these
displacement?
two lines intersect. So whenever those two intersect.
Yeah, but what should the first one be? But displacement relates how to this. See what I'm saying? There's a lot to dig into there. Got it? You guys doing all right here?
No,
Which part are you on?
I'm still on A,
Oh,
because I thought that this was the
Yeah,
answer.
yes, but you have to figure out delta x1 and delta x2, right? Do you know
Then I
it?
try to go to find T right here, but then my A is
So you gotta follow the procedure. List this, good. List your equations, get equations for delta x1 and delta x2, and then do the subtraction.
I see,
Right? If you agree right now, as it's written, you don't, you see what I'm saying?
yeah.
So we're
I
doing the
see.
same procedure as every other problem, because now we have to layer it back
There's just
at the end. Cool.
Mm,
And
Okay.
maybe you could use this information. You agree that your velocity relates to time and acceleration with some kinematics equation?
Yeah.
Probably need to use this equation to get the time. And then use that to get the x, and then do the subtraction.
Oh,
Got it? Yep, yep. You get there?
I think so. I'll figure out what
yeah, but X is
the displacement
Yeah,
right here,
okay.
and I'm getting this right here.
So they have the same time.
speeder.
Yes.
Yeah, so that's cool. So that's what's cool about this one, is that you can use the same time for each side, so you can drop the subject. Like
And the
this.
velocities are the same too.
So you can set the v's equal, get
Speeder
the
doesn't
t's,
change.
plug in the t's, the x's. Yeah, yeah.
I'm
Maybe I'll
better at
put-
doing problems with numbers. When I do stuff like
Exactly.
this, it screws me up.
Exactly, because you have to think more this way, and you have to do algebra, right? This screws everybody up.
Yeah.
That's why I'm doing this for you, and this is what your test questions look like.
Oh, this sucks.
Yep, have fun. Now, here's the deal. If you practice, you'll get good at it.
Yeah,
And then what will happen is, I know this sounds crazy, you will eventually come to like this method more because it's less writing.
Yeah.
Right? And then you're only putting in numbers at the end or in a code or something like that. So I know it seems crazy now. Just trust me, eventually you'll be like, oh, I'm so glad I'm not doing numbers, but it probably won't happen until about week 12.
nice.
All right? That's how long it takes to get used to it. Yeah, question?
I think I figured it out.
Well, did you check with the solution?
Not yet.
There you go. I'm gonna make some notes up here.
Yeah,
So,
and
because we don't know.
so since we have we're given the velocity, the initial velocity, is acceleration.
We don't.
We don't know.
It's still be the same. That's fine.
We can
So
use kinematics for this. But even-
Velocity. So. We would have to find the time channel this first.
Yeah, that's what we like.
Yeah, yeah. Yeah. Yeah, but it's.
Hey, Jules, how does that show up on Zoom? Is that too small on the subscripts, or is it okay? It's okay. I'm gonna see if I can get it just a little bigger, and then it's like right at the edge, huh? But there, is that all right? That's the best I can do, I think, to get it on there.
All right, so I see a lot of people kind of struggling here. Maybe I'll talk about this again. If you're in the zone, you don't have to listen to me, but let's go through this. So what is our procedure? We drew a picture, right? Somewhere over here. I apologize, you can't see it on Zoom, but we drew a picture and we kind of got to thinking about it. Then you might list a bunch of these things, right? So I don't know X1, but I do know this is B, this is B, this is 0, and I don't know the time, right? Similarly, this one, I don't know. I do know the cop started from rest, but I don't know the final speed. But I do know the acceleration of the cop was A, and I don't know the time. But one thing we could do is we know that this is an unknown, and this is the same unknown, so we could use the same letter T. Agreed? So just, is everybody okay with that set of knowns and unknowns? Okay, so now when you come over here, why is this useful? We can erase the subscripts because we know they have the same time. That's going to save us a little bit of effort. What is one thing you could do before you get ahead of yourselves? Plug in whatever is 0, because that makes the algebra easier. So in this case, I'm going to use an eraser. Basically, anywhere there's an A, I can erase it. Right? Because A1 is equal to 0. So I just got rid of all of the A's. That makes stage 1, or the equations for 1, look a lot easier. Over here, what parameter can I get rid of? What was 0 for the cop? V2 initial is equal to 0. So that means I can get rid of this, and this. Already, this is a tremendous reduction of scariness, so to speak, right? Plugging in what is 0 first thing can reduce the stress on your brain and the amount of difficult algebra you have to do. Okay, at this point, let's just check what we know and what we don't know. Do I know X1? Do I know V1? Do I know T? Let's keep going. Wait a minute. This is just nothing. This is just nothing. So notice this. When A equals 0, the only useful equation is distance equals rate times time. Okay, that's cool. Now, wait a minute. I thought it was displacement. You're absolutely right. But if there's no acceleration, you're not reversing direction. That's why we could say distance equals rate times time in grade school. All right, over here. Let's take a look. Do I know X2? Do I know A2?
Yes.
All right, and T is unknown. Do I know V2 final? In this part, in part A, do we know it? Yes.
Oh, yeah. B.
V2 final, whoops. That is the key word here, right? This is true for part A. That's a piece that if you don't use it, you're never going to solve the problem. So we do know it. Do I know the acceleration? What can I figure out? Once you know time, can't you get x1 and x2? Done. You see it? So I know maybe you don't like doing these checks and question marks, but for me, it helps me organize instead of just trying to flail about randomly. It gives me a plan of attack. I'm like, well, this equation I can figure out. And usually this is true. If you can get one parameter out of this whole list, oftentimes the rest of the problem just falls apart and you can get it. Did that help any? Okay, now down here, let's see if we got this. I know this. Oh, look at this. The last equation, I could get x2 directly. So you might be thinking, oh, this is great, but notice we still need this one because without this piece, we can't get that piece. Got it? All right, I want to show you something here. Go ahead and keep working for a second. We're almost to the break. Hang in there, all right? Writing out those equations, plugging in the zeros, checking what's known and unknown. The system works pretty darn well. Tremendous number of problems. And like I was telling another student, even though this is painful at first, in the long run, it's faster to do problems this way. You may not think so right now, but in 10 chapters, this will become the way you want to do problems. But it's going to hurt for a little while. Screen share. And if you want, I know you're excited to work, but maybe give me your attention here. Sometimes the real world is difficult, right? Like the fan cart and this, whatchamacallit over here? Constant velocity cart. Sometimes it doesn't show it as well. So maybe when you look at this one, it might help. So in this case, oh man, I got lucky. The red is supposed to be the cop and the blue is the snail. Sorry, I switched the order. But when we run this code, this is supposed to be like a slow-mo version of what's happening here. Right? At some point, the cop will catch up. Now notice when you look at this, I don't know if you can see this very well. And let's see, I don't remember what units I plugged in, but let's just go with this for right now. We see a couple of things here. We see that the snail is moving. Notice the distance between these markers is constant. That's a sign of constant speed. Right? The distance between markers is identical. Now notice what happens with the spacing of these adjacent dots. We see the gap getting wider. And then by the end, look how wide this is here. Right? So we see that the cop is obviously speeding up. And then if we could go down below and look at these graphically, right? Oh, now all of my annotations right here. You could see what the position versus time looks like. And in this case, right, to be clear, this is the snail. And this is the cop. Approximately at what time do you see maximum separation? Where do you see maximum separation? What's that?
Around 4.
Around 4. Do you agree? Right here, look, the gap between these two lines is biggest. So this is max separation. So far, so good. Obviously, you could do the same thing with a plot of v versus time and see what that looks like, and that's done for you in the solutions as well. if you're curious, I'll show you really quick what's inside the code. If you want to take a break, this is a good time to take a break. If you want to finish up that problem, whatever. So if you're curious here. So Jaden helped me clean up the code, so credit to her, right? So this is a term we haven't learned about. It's momentum, but whatever. All right, so we've got, oh, wait, in this case, oh, I called that position. My bad. Sorry, it's been a while. But you can see in this case, that's just cosmetics, cosmetics, cosmetics. If you go down into the code, right, you could easily change this code to show only maximum separation. Right now I'm showing when they catch. If I wanted to show maximum separation, I could just change this to what? If I want to show maximum separation and stop the code, probably ball.v is less than ball.v, right? That would give us the maximum separation if I coded this right. Oh, I might have called it velocity instead of v. So I'm going to go back here and change that out. Anyways, all right, so if you want to see this, I'd have to go look what I called v. Oh, I might have called it v1 and v. All right, so whatever. Sorry, it's not exactly the same as the other codes. Oh, I called it veloc. All right. Fix that up. Sorry. So we run this one. Hopefully now it works. Oh my gosh, there's probably some other. All right, whatever. That's what I get for trying to edit the code on the fly. So this is a good time to take a break. But yeah, you get the idea here. Sorry about that. There's probably some other reference that I got to clear up. All right, so go ahead, take your break.
What was there? I was like, right.
I was trying to put Play-Doh, but then the Play-Doh.
There's probably something else in there. Yo. What's up? Oh,
Oh, it's still going.
yeah. Did you break it?
The big one.
This one? No, because it was at EP's.
They should have.
And I got the hovercraft here, so don't let me forget it yet, all right?
Oh, show me this one. And I was
Get it right.
like, bro, this is not major.
And they're like, wow. Who did I send that video
Is it
to?
like those?
Maybe it's in my basketball group chat.
Or is this like one of those hoverboards? where, like, they say hoverboard, but it's just.
Yeah. Wheel, between two wheels. Or you can use that, this rail and get something that covers it or just cover it. I remember we pushed it in the lab using these rails and then like you push air in it. So it creates a kind of. Frictionless, surface.
Is this your favorite part, George?
What's that?
Is this your favorite part of the lecture?
What- I know, right? And I have to clean it twice, but for me, I can't help it. Like, I don't know about you, but I just can't stand all that those ghost marks, right? So I hope, I mean, do you guys feel like it's worth it for me to make sure the board is extra clean like this? Do you notice it or not?
I like it.
Yes.
I just hate that ghost imaging on there, right? It just distracts me and then
OCD kicks in.
yeah, well, I'm focused on the wrong things then, right? I gotta focus on, like, so if it's super clean, and I apologize if it's not perfect, but, you know, I'm trying to get the best of it. So anyways, all right. Let me just do a gut check on you. What do you feel? Do you feel like you have an idea for how to approach two-stage problems? Right? It's all about doing the algebra and getting the equations and looking for the connections, right? Just give me thumbs up, thumbs down, thumbs up. Obviously, you need practice, right? Okay, so I'm not lying to you. 2.36, 7, and 8. If you do all three of those, they get incrementally harder. So, and that's like all the tricks that I usually think of on testing. So if you can actually do those three problems and get used to those three tricks, you should be all right. And on the flip side, if you don't do them, you will probably get a 0 on that problem on the test. Because if you just don't practice it enough. And at the end of class today, we'll try to do the hovercraft, and I'll also show you some old tests real quick so we can see where we're at. And you can see that we're getting there. All right. And you can see the types of things that I do on tests and be like, okay, he's not lying to us completely. We might have a chance. Okay. So that said, I'm going to skip to the other topic. Yeah, let's do that. Let's go to page 49 in the workbook. Okay.
It's very fun.
Okay. Focus. So first off, you know this fundamental equation, A equals dv dt. And we could actually use this as a vector as well, but in 1D, we could take off the vectors, right? You could say A sub x equals d dt of v sub x, or we could even drop the x subscript and just say A equals dv dt. So again, we're doing one-dimensional motion for this entire chapter. Now, in this case, this is technically called a differential equation. That's what that's called. dv is called a differential. You could call that differential velocity. dt would be differential time. Okay, so those are the differential equations. Now look, here's another thing. If A is constant, we know you get an equation that looks like this. That is the equation that we know, and we showed that using calculus. If you're curious, I'll rederive it very quickly. We know that A equals dv dt. So I could cross multiply and switch the sides. What did we do at this point? Do you remember what we did to keep going? If I wanted to learn about the velocity, what would I do? Integrate both sides. You go from initial to final, initial to final. This side, what does dv become? Not v, but
Change in V.
yeah, change in v, or v final minus the initial. This side, that's going to be a times t final minus a times t initial. Just kind of plugging it in. You can just watch. You don't need to take notes. You got the Zoom if you really care. You can read your Bibles. Moving this around, typically at this point, we would set t initial to 0. What's a good name for t final in most of our problems? T. And then we can rearrange this, and we see that v final is equal to v initial plus at, right? And then we could do the same thing again, where we said v is equal to dxtt, and we can take this, plug it into there, and do the integral again, and we get this result. And we can do that in a minute if you want, or you want to see that? Okay, let's do it. Let me just go over here a little bit. Let me get some more board space. Okay, so let's plug this in, right? Now I see, if I want, I can do this. Dx dt is equal to, well, the velocity as a function of time is this. Think about it. Think about it. Give me your attention for just a second. If you tell me the time and the initial conditions, I'll tell you the velocity at that time. V final is the velocity as a function of time. Take a second to make sure you believe it. If you plug in the time and solve for Vf, that is the velocity at that time. That's why I could shove that into here, right? Right? Now what am I going to do? There's a t over here. I'm going to cross multiply. And then I have to remember, I'm not just multiplying it by the v or this, I'm multiplying it by the whole thing. I have a differential position here and a differential time here. What could I do to figure out the next step of this equation? What have we been doing? From initial to final. Right? In this case, what do I get on this side? Delta x, or x final minus x initial, right? What do I get on this side? Well, when I integrate v, well, let's just write it out. I'm going to get v initial times time plus 1/2 a t squared evaluated at t equals 0, or t initial, and t final equals t, right? Well, when I plug in the 0 limit for this case, I get v initial t plus 1/2 at squared. Solving this for x final, I'm going to pause here. I just whipped that through really quick. I'm sure you've seen this in calculus class or in some other high school physics class possibly. And I've got this written up in the solutions as well. So if you're like worried that I was going too fast, you've got the YouTube video. Let's pause and see, does this basic problem make any sense? Or how are you feeling about the calculus here? Just give me a thumbs up, thumbs down. I'm not offended if it's down. Okay. What we were actually doing here is the process known as separation of variables. Let me show you what I mean. In this first step, there's not much going on. Everything's constant. But I want to focus on this step. Look at this. There's a t on this side of the equation. I better get the dt with the other t before I integrate. I'm separating this differential position variable from the differential time variable before I integrate. That's the concept known as separation of variables. So far, so good? Yes.
So V is not, since V also includes time, don't we have to, with the initial?
Absolutely. Do you agree that V, so follow this step. I took this equation for V and plugged it in right there. Do you agree that this is equal to that, which is this equation? Just
Yeah.
you good with that?
So it's when you integrate it, it's where like my question is, when you integrate the VI.
Yeah, yeah, yeah. You'd make two separate integrals, right? Right? Isn't this the same as the integral of V initial dt plus the integral of A dt or AT dt?
Yeah, so you see that with the time one, it makes sense. You do all the integration stuff, but isn't V also like based on time as well? Like the
VI is a constant.
Yeah,
Oh,
this
yeah.
is not V, this is V initial. So take a look. You're absolutely right. V is not a constant. V is something that's changing
Yeah.
according to this equation. So in this particular problem, I took the equation for time and plugged it in, but there's only one initial velocity. Agreed?
Yeah.
That's why I'm not integrating. It's not, what would I call a circular reference?
So
Is that better?
Yeah.
Excellent question. And again, in this, we assumed A was a constant for this problem. That's why we could just pull out the A and do the integral. All right, so the goal here is now, okay, I want to actually understand non-constant acceleration. So in this particular case, let me go back to what we're talking about here. So actually, let me do it this way. This process, the process we followed was called separation of variables. The answer that we got is called the solution to the differential equation. So if I can go back to board one, come on. Come on. Right? We have several different pieces here, and I want you to know how to communicate with these pieces. This is called a differential equation. These pieces are called differentials. This process was called separation of variables, and the final result is the solution to the differential equation. So this is the solution to the diffie-q. All right, everybody know the names of the different things? So usually, why are we talking about this at all? Generally speaking, in life, you could usually come up with a differential equation from a free body diagram or some other physics, okay? And then the problems in life, we usually want to understand the solutions to differential equations. So it's oftentimes easy to write down differential equations in physics, and then one of the goals of physics is to solve them. That way we can understand the behavior of the position as a function of time. Notice in this equation right here, if you tell me the time, I'll tell you the position. So what we have found is x final literally is the position as a function of time. That is the solution to this crazy. Okay, so far so good? Now, most students say, oh, it's freaking easy, man. I'm just going to integrate the velocity to get the position. That's not always going to work. Let me give you an example. Okay, look at the example on page 49. Okay, I'm going to erase the board here. I'll just show you the one mistake students sometimes make, and after you know that, you should be off to the races. So example, page, what did I say, 49? We were told that the acceleration is equal to some crazy looking equation, 6t squared over v. Okay, So let's pretend there's some weird physics phenomenon that says, aha, if I know the time and this velocity, I can figure this out. So far, so good? So just pretend this is a real physics formula that somebody figured out doing some physics work. Well, the first step in this problem is to write the following. dv dt is equal to 6t squared over v. Now, if I just crop, this is what pisses me off all the time with students. They'll be like, hey man, I'm just going to multiply by dt and integrate. That is completely wrong. You can't always multiply by dt and integrate. This is not valid. No, bad monkey. Okay, bad, bad, bad. We must separate the variables. Okay, that means I don't just get the t's with the t's, but I must also get the v's with the v's. That's the extra step that sometimes students forget. Look, v should be in a v integral. T should be in a t integral. So if we do this one extra step, then your modeling is correct. See the subtle difference? Now, when I integrate, I know what I'm doing over here, and I know what I'm doing over here. This is just a t integral with some constants. This is just a v integral. If I had done it the other way, look at this. If I said dv is equal to the integral of 6t squared dt over v, that is a valid statement. But do you know how v depends on time? This is what he was saying earlier. This is not v initial anymore, is it? This is v. I don't know how the velocity changes with time. I don't have a function to put in here. I don't know how to do this integral. It's a correct statement mathematically, but we don't know how to solve it. Does that make sense? All right, and that's the crux of this. All right. At this point, I would always stick on initial and final, initial and final. When I do this one, what do I get on this side? V squared over 2, evaluated at initial and final. On that side, when you integrate the t squared, you're going to get a cube. What is that, 2?
Yeah.
2t cubed.
Evaluated at initial and final. Now, because we're doing physics class, instead of doing plus c all the time, just trust me. Get in this habit of always putting in the definite limits, initial and final. On this side, I'm going to get the final squared over 2 minus the initial squared over 2. On the other side, this one, we almost always say t initial is 0, right? Usually a good time to start a clock is 0. And this one is going to become t. Now you might be saying, why don't you just write 0 and t in the limits? Strictly speaking, t is the variable we're using inside the integrand. That annoys me because if you have a t outside and inside, it's confusing. It's not mathematically rigorous. So what I like to do is just go from t initial to t final. After you do the integral, then say t initial goes to 0 and t final goes to t. That way we're not making a math error. Is that okay? If you care about this, talk to me afterwards. So in this case, the initial limit should go to 0 in this particular case, right? Now I'm going to write it there. One of my other pet peeves with students is the following. Students think every initial with t equals 0 goes to 0. It's not always true. Always, always, always plug in the 0 limit and check. If not, you lose points, and it drives me nuts. It's like you did all this hard work, and then you forget to plug in a limit, and that's why you lose points. Bad point. All right. Now at this point, oh, go ahead. What's up? Or
When it's like cosine x and like your brain, like when you're like always, I felt you hitting me. I was like, I felt that.
yeah, because you've probably done it, right?
I do it all the
We've
time.
all done it. We've all done it. We've all made that mistake of forgetting to check if the 0 limit is 0 or not 0. Here's the deal. In your calc classes, they always start you easy, right? Polynomials. What could be easier? what about logarithms, exponentials, trig functions? Almost all of these have some non-zero answer when you plug in the zero limit. Whatever. Okay. Now we're almost there. What is our goal when we're doing the separation of variables? Do you remember? We started with a differential equation. What are we trying to get to? The solution. Is this in a good form for the solution? Not so much. What is the solution? If we have this equation, we're talking about acceleration, how it relates to velocity, or this differential, the solution would be solving for what? The final, which is also velocity as a function of time. That's what we're trying to get. As the function of time. There we go. That's our goal. So what am I trying to do with this equation? Solve for V final. What's the next step you would do?
BI square root solve.
Okay, yeah, I was gonna multiply by 2 first and then move it over, but yeah, get it real quick. You can do whatever you want. Right, I'd multiply by the 2, you can move it over. So what's the final? Not quite. It's physics class. Plus or minus. Yeah. I don't know if you've noticed this in the homework. Anytime you take a square root, just like I'm saying, always check the zero limit, always check both roots of the square root. You know what I'm saying? Now, in this case, right, if the object was moving to the left, we would probably want to use the negative sign. If the object was moving to the right, we would want to use a positive sign. So in this case, there's a reason that maybe you would use these different symbols. So far, so good? Yes.
So we're gonna be doing more differential equations.
Gosh, it's almost like I wonder what differential equations we would use in a physics class, don't you? Turn the page. Okay. On page 50, I do more examples. At the bottom of the page are the 10 main differential equations we are going to use in physics 1, 2, and 3. So on page 50, right, we use these in different cases. You can also use separation of variables to determine the energy levels of the hydrogen atom from the Schrodinger equation. I didn't bother to write that one in there because I didn't want to scare people. But yeah, that's a problem. Like chemistry, the periodic table can kind of be figured out with separation of variables. If we're a little bit loosey-goosey there, right? So yeah, there's a large number of cases where you could use separation of variables. Similarly, maybe there's problems you can't use separation of variables. You can use other techniques that you learn in Math 184, or you can learn how to code. And then if you know how to code and Math 184 and separation of variables, you've got all these tools, so different problems require different ideas. Then you can learn Monte Carlo sims and just know a lot of different techniques.
And you get paid 6 figures.
Hopefully, yes. And then bring me a briefcase with $1 million every couple of years. I'll even throw Dom a couple of bucks too. Or I'll just barbecue for him. Yeah. That was actually Dom's old retirement plan. Wasn't it? Like every former student had to give you like 0.1% or 1% of their future earnings.
1% is fine, he said.
Yeah. I'll even take a 10th of a percent. Hell, I'll take $50. Anyways, all right. Is that good?
I feel like that should be a thing though.
Yeah, well, you guys shouldn't have to pay so much for school either, but you
Oh,
do.
that's also true.
So, yeah, don't give us any money. All right, yeah, school is way too expensive and it shouldn't be, but not here, right? You're getting, no matter how bad I am, you're getting a good value because it's so cheap. This is why I'm here. All right, let's focus. We've got, what is this? About 20 minutes left. So let me show you, look at page 51. Somebody asked about jerk in the class, right?
Oh.
Not only, was that you?
That was me.
Look at problem 2.53, right? And you mentioned something about a cosine function. That's 2.54. So on page 51, Those are simple ones where all you have to do is just integrate and your shortcut without having to separate would work. Look at page 52. Those of you that are doing air resistance problems in class might recognize these. The most common equation in physics at this stage that requires separation of variables is when you have a drag force, right? So here's a huge set of examples, right? We could have low speed. Technically, we should probably say small Reynolds number or something, but I don't know. You could say the resistive force is minus BV, where if this is, or here you could say resistive force is equal to minus alpha Vx squared. So basically, the faster you move through a fluid, your drag can either be proportional to a linear velocity term or, but I just want to point out, I know we haven't discussed this yet, but if force equals ma, think about this. If you plug in these forces, we get minus BV equals ma. There's a differential equation that requires separation of variables. And I think that was the spirit of your question, was it not? Here is another one right here, right? You can say minus alpha v squared equals ma. And then again, we see that a is dv dt, separate the variables, right? Get the v's with the v's before you move the t's around. Here, get the v's with the v's. So these are actually two somewhat common physics problems. And you might be saying, well, dude, why don't I just code it? It's easier. Here's the deal. If you code something, it's nice to have a way to check your code to make sure it works. So if you can derive the solution exactly, then those of you that are doing air resistance, who is the other air resistance group? Are they in here? Whatever. Is it you guys? Whatever, whoever it was. But the idea is you could use the results and then you could say, look, here's the plot using the exact equation. Here's the plot using my code. If the two plots look about right, that means it's a good agreement between the coding theory. All right. Do a problem off one of these pages, right? So try one off page 51 or page 52. If you're bad at it, have the solutions open. We're going to circle around and help you. Okay. Like you might want to try 2.54. I think that one might require a t equals 0 limit. I don't know. And then the ones on page 52 require separation. So if you have a lab that involves one of those, maybe you should do that question now. All right, all right. So I'm going to circle. Any questions on Zoom? Yes, correct, Maria. Correct on both counts. Sorry it took me so long. Okay. Yeah, have the solutions open, see how you're doing. Anything else you want to say about this, Jules or Dom? Or did you use this in 162 on occasion, probably? Okay, yeah. And then I know we used it in 163 for like RC transients, RL transients, right? That was when we mainly did it. Yeah. Dom, anything you want to say about these? Okay, got it. Huh.
Educational.
So that's your way of calling it long. Wait, you got an idea? All right, I'll give you a second, get rolling. Does that address your question?
Yeah. So we got a bunch of different.
Yeah, Taylor series, power series solution, the method of convenience. Yeah, yeah. And as time goes on, the method of Wolfram Alpha is pretty good too.
Right? You know what I'm saying?
I don't remember that one.
Well, you just plug it into Wolfram Alpha online and it does it all for you.
Oh.
Right? But like with anything, if you don't know how to do the basics, sometimes it's very difficult to check your work. Have you ever seen Wolfram Alpha online? No, just plug it into that part, it pretty much does it for you. It shows you a step-by-step solution. So, yeah, I still think it's worth learning this because we use it in a number of times in a number of derivations, and I think it will give us a physical understanding on rare occasions. But yeah, it's like,
But we don't go past like separation of variables.
no, I'm not going to do method of convenience or any of that. That's like genius. Cool. Yeah. We're going to stick with this one because it does most of what we need to do for the basics.
So it's like the first thing you learn.
Yeah, is this like the first day?
It's exactly like computer.
Yeah, exactly. Good. How are you doing? All right?
I didn't have to give it.
Okay, gotcha. Hey, Jules, how are you doing? Staying awake? What's that? You don't miss this? Yeah, it's funny, right? Like, if you get good at coding, you never need to do this. Yeah. How are you doing?
I know.
Good evening.
Okay.
You feel that I could do this?
Come back in a minute?
Yes.
Yeah, you're just getting started. What do you think? You guys have an idea how to get started? Right, I like it. Remember that code. All right, cool. Here's a good trick, right? Rather than overthinking it, when you do your integral, take a guess and then just check if it works, especially with sine and cosine, because like the plus signs and the minus sign.
Oh, yeah.
And then the omega, is it 1 over omega or is it? Yeah. What do you think? You got some ideas? Oh, okay. Oh, yeah. Awesome. Glad that worked out last time.
I'm just looking at this one, determining, trying to find factors of
What are you
Oh, this is-
You're doing?
the declination, no, declination and acceleration. So like your example was the constant.
Okay.
I was doing this one because because I had a constant alpha,
Yeah.
negative t.
So when you get to the other page, make sure you do.
That was
Linear thing. So I think the linear thing is the one that turns out, to be- this is the same, gives you the actual result. This one is actually.
Do I have to separate the variables? Yeah.
Okay, and then what the b do the e?
Yeah, well, that's a beta. So alpha and beta.
Well, it's like alpha, that can just be something that was going to see them just
Well,
How did you separate them?
the units on this one's going to be per second, that's the velocity.
units of that is gonna have to be-
Per second squared.
Yes, exactly.
Then like what, what's
So
the
that's
beta?
probably an acceleration. This is a decay rate, which is acceleration.
But then how does this affect the t? Like, if this is in a power, what does that do to units?
Oh, so remember, the exponent has no units, right? The argument of the exponent must also have units, so beta must be one of the. Does that help you?
Yeah.
Yeah, so that's the cool trick. Is we know the exponential itself has no units, except for the units of alpha. We know the argument of a function has no units. Is that good?
Yeah.
Similarly here, right? This is a function. A0 is clearly the initial acceleration. Here, omega must have units of 1 per time. So for like yeah, good.
So this is, so I can, this is like acceleration and this is just.
Something like that. Something like that. But it's different because of that linear term. So it's not gonna be an exact match. Whereas this problem, I believe, turns out to be an exact match. Yeah, exactly. So,
I didn't hear.
yeah, exactly. And I think when you look at the solution, you double check on that. I just mentioned that because this one, I think it gets nasty in a hurry. So, just right, yeah, I'll let you see.
I'll just look at it.
Yeah, exactly.
I'll just see what kind of
Use
mess
the
I'll do
solution,
myself,
yeah.
and I'll just casually flip the page.
I think they had a question. right there.
Yeah, I have a question here.
Okay, Julie's on. What's up?
What do you need?
So,
All right.
eight knots would still be TV over
Should I get some space? Okay.
Integral of acceleration.
What do you think?
Yeah, because we have to find the velocity as a function of time.
Very common, right?
I don't know if I'd say fun.
I used to go to math competitions when I was a kid, right? I used to do all kinds
No,
of
no,
math. I like math.
we have to find the velocity.
I like the
So we have
puzzles.
to take the-
I like what I can do.
Yeah.
Yeah, I think, just give it a whirl. What do you think? Oh, that's the.
Yeah, so
say
dA
again.
dt is velocity.
Yeah, so that's the initial position. So like, you know how when you plug in all that crap, there's gonna be an initial and a final every time?
Yeah.
So when you do the integral, you're gonna get,
No,
like, on the first integral, I think you'll get A initial and A final.
A.
Well,
no,
what I'm telling you is that you could say A initial is
to be dV over dt, right?
And then when you do the velocity initial, there's gonna be a v initial. Like, let me show you.
Like, use that the operator you usually?
Like when you did all this integral, what I'm saying is, let's say you got to this answer. I'm telling you that the initial for this problem that you're doing was supposed to be called V0. It's just, that's just the term that I chose. That way you could read the solution. I chose this called V initial V0 for that problem. Sorry. Does that make more sense?
Yeah.
Wait, how you doing? Get it done? Yeah, and then T is 0.
I think this looks like you would have to use,
Is that good?
integration by parts.
Alright. So that's
But
A.
like,
Now, how could you do the velocity equation, position equation? Right? Nice, nice. Yeah, you're right.
Because how would you integrate,
All right.
because
A initial
A
0.
isn't a constant, right?
No, look. Call it A0. We'll just call it A0. Okay. It's sort of, remember when you did these problems up here? Right? Like when you did this one? Like the initial velocity is not necessarily 0. So in that problem, I said the initial acceleration was A0. Okay, is that good?
Yeah.
So it's actually going to look exactly like this, except it should be A naught, J, T, right?
Okay.
Yeah. Get it?
Yeah, well, not really, but I'm just trying to understand.
Follow the procedure.
the procedure.
Okay.
Yeah.
So you're right there, right? This is your equation. Start with that, write that right here. The ADT equals J. Now J is a constant, isn't it?
Yes.
So separate the variables, get the A's with the A's and the T's with those. So just cross multiply by dt, and then you say the T's are separate from the A's.
Yes.
Then you can just integrate.
Oh,
Got it? So remember, you're always wanting to do separate, then integrate. So in your case, right, in this problem, I had to get the V's and the T's on different sides. Because this is a constant, all you have to do is just cross multiply the dt and integrate. So this problem, they're already separated for you, basically.
yeah, I got it.
Move the dt over. What do you think? Getting it?
I'm not sure, because the way that I'm looking at this, it looks like I need to do some type of integration by parts because I'm multiplying. But I think I'm like completely overthinking.
Yes, you are. Okay. Help me out. What's the derivative of sine of t?
Cosine of t.
What's the derivative of cosine of t?
Negative sine.
Okay, so we got that. So once you know that, the rest is solved. So now let's say, what's the derivative of sine of omega t, where omega is some constant? Well, the first part, it's just the, whatever, the chain rule, right?
Yeah.
So I know I'm going to get cosine of whatever was there times the derivative of what's inside. What's inside? Omega t. So what's the derivative of omega t? If omega is a constant,
Omega.
omega. Well, what do you think the derivative of this will be then?
Negative omega
Times S.
sine omega t.
So what do you think the integral of cosine of omega t is?
Cosine of omega t would be negative sine, no, negative omega sine.
Remember, it's the opposite of the derivative.
Oh, the derivative, sorry, sine.
So, right, I know that if I take the derivative, so I know that's gonna be this, it's gotta be gonna relate to
Sine
that.
omega t.
Now, when I do the derivative, and omega pops out front. When I do an antiderivative, it should,
Oh, that's right.
right? Now think, I'm not sure if I did that right. So let's check. Take the derivative of this, see if you get that.
Oh,
When you take the derivative, I get a cosine, the omegas cancel.
Yeah.
That's what I mean by just kind of, you don't see, start here, get your minus signs right. Then do this, because it's easier to do the chain rule than to try and integrate opposite upside down. And like, and then you just kind of double check every time, because it's easy to miss a minus sign and it's easy to flip an omega. We have one more tool. Check the units. What are the units of this?
Should be no units.
No units. What are the units of this? Time. Differential time is still, it's like a nanosecond, but it's still time. What are the units of this? What were the units of omega in the problem? So this is 1 over.
So it will be second to radians.
So in physics class, where we actually talk about the units all the time, it's actually easier to check because you got one more way to check your integral. Make sure you didn't flip something upside down.
Yeah.
See what I'm saying? Good?
Yeah, I'm just lost because this A naught is throwing me off.
It's a constant.
Oh, it's a
Did
constant.
it say what it was?
No, it just, or yeah, it did.
With
It's
a
seven
constant
over-
A naught.
Oh, my gosh.
Yep. That's
I
the
was-
second step, read.
Yeah.
But that's all right. So this is the thing. Do you agree? This is kind of what you have to do is when you do a physics problem, you get started and then you just reread the problem every once in a while. Be like, wait, was that a constant or not? Did it say state? Just get in that habit of constantly rereading the question to see if there's some piece that you missed or clarification. Now, to be fair, I mean, every once in a while, an instructor will forget that you could ask a question during the test. And no shame in that.
Yeah.
And oftentimes the instructor will come up and say, did you think the first sentence?
Yeah.
But yeah, right?
Right.
So you'll get in the habit of catching it, right?
Yeah.
Furthermore, you're going to be using my questions because these are all written by me, so you get to know my habits and where I put things.
Yeah.
So you'll get used to it and you'll get used to me.
Okay.
Okay.
Oh my gosh, I literally would have done that in 2 seconds if I would have read the problem.
Yeah, yeah. So yeah, that's the thing. If you're not sure, reread it, check it. Good.
Got it.
All right, all right. What do you think? How'd you do? It gets nasty in a hurry, doesn't it?
But then I don't understand, because I was looking through the solution for that, but for 57, what are these for? Why are we multiplying?
Oh, here's the deal. There are many different correct ways to do the algebra set. I just chose to do it that way to avoid the reset. Right? The thing that I'm doing here is like, I'm trying to clean this up. Right? I'm just like, man, they don't really like this V, negative V, if I do it this way. Hey, look, it's like, when I see this line, this looks easier for me to integrate in my mind than this line right here, where the V is with the negative constant. See what I'm saying? This tells me when I have V isolated and positive, I don't need any use of, I shouldn't expect it minus sign. That's why I chose to do that. Is that required? No. So it's just my style.
And I was just like, why
Yeah.
is there extra numbers in here? Because otherwise I would just have like use something out down here. And I'm like,
Yeah. For me, when I see this, it looks like I still needed a use of anyways, but the use of was easy.
the use of is just positive. It's not
Yeah, exactly. So now I'm like, so in this case, my du equals my dv, and that's an easier use of for me. So the other way I could do it is, I know if I have v minus a constant, the integral is just, I haven't done it. I just haven't done it so many times. Is that cool?
Yeah.
So it's basically, just from experience, I know that works out best for me. Doesn't mean it's right.
Yeah, I just wanted to ask that.
Yeah, yeah, yeah.
Why?
Is that cool?
Yeah.
Yeah, yeah. I like that style of integration. Keep working. I'm just getting something up here. Got that medicine ball on that? Dom on there. It's always nice to end class with some good news. So I know you're right. You can tell you got some work to do on this probably, and there's plenty of practice problems for you. Probably going to do another one like this in chapter 4, which is our next chapter, but I wanted to end class by showing you some stuff, okay? Screen share. Looks like that's kind of showing up. All right, so it's almost time to go. I want to do, I've got the hovercraft over there for you, right? We could do that afterwards. But I wanted to show you some stuff that we've been working on and show you the exams, because a lot of times students are like, okay, just tell me what's on the test, right? Okay, here it is. I just want to point out some of the things that we've been doing. Okay, this is next chapter. So we've still got some more stuff. We've started talking about this. We've started talking about these things. We've talked about vectors. We've talked about sig figs, notation. Let's just look at some of the old tests and do some problem identification to show you that we've been doing things that will show up on the test someday. I'll just make that back up. When you look at this one, this is a chapter 1 problem. It's basically check the units for the constant K. Okay. This is a problem where you could do some dimensional analysis or some geometry and equations. Also chapter 1. Notice you have to get this right. Notice it's worth a lot of points, right? Because I could take off if you don't follow any of the instructions, right? And if you want to get partial credit, you better show some significant work. Here's one. This is a chapter 4 problem, but it's basically a vector addition problem that we will discuss in chapter 4 next week, or wait, next class. Look at this one, a vector. Do a dot product and a cross product and get an angle between. Okay, that's chapter 3. Here's one, plug in some numbers from chapter 1. Can you plug them in right and do the math right with correct sig figs and units? Oh, here's a graphing question. This looks like one of the 29 in a fraction that we kind of mentioned you could look at if you needed conceptual understanding. Which objects have negative displacement, right? If we're looking at an XT graph, you have to think about what that means, or negative initial position, right? So you're having to think about a graph and think about what's the concavity, what's the intercept, what's the slope. Here's one where I ask about moving forward, slowing down, or et cetera, right? Here's one where it's a VT plot, same kinds of questions. And this is chapter 4. This looks like what we just did today. Look at this. You have object P and object Q. One of them has an acceleration until they reach speed V, and then it continues at constant speed. So this is like 2.37, the cop and the speeder version 2. The other one has a constant acceleration of this rate, and then figure out the maximum separation distance. That's something we talked about. Oh, here's an extra credit problem where you have to do separation of variables. That's one test. Let's look at the next one. I know it's time to go, but I just want to show you this one thing here, right? This is a chapter 4 problem. It's similar to what we did today. We'll learn about that next time. Here's a plate with an area and density and a conversion. It looks like a conversion. Look at this, a unit conversion. Here's something. Can you plug in the numbers and actually do it right? Here's a graphing question where I give you a graph. Can you get the velocity? What time, right? We talked about this last time. This is a chapter 4. Don't freak out on this. Okay, whatever. That's a chapter 4. Here's another one, right? We're seeing some of these problems. If you got to get out of here, that's fine. I understand. But I hope you notice, here's another relative velocity addition. Seeing most of these problems. Oh, this is like what we did today, right? Where you have 2 different accelerations and it's 1D motion. Let's see. Extra credit with separation of variables. Are you noticing a pattern here? Right. One more. And then you could look at these later to your heart's content. Plug in the numbers. Can you do it? Get the units. Do a conversion. Oh, this is the first year I gave that. Yeah, all right. Here's a 2-stage problem. Cop and a speeder. Okay, make the plot. Got it. Do separation of variables. Chapter 4. All right, anyways, I'll leave it at that, but I want to point out, hopefully you're getting a feeling that this is some of the stuff we've been doing in class. If you do the homework, then do the practice test, right? Use the solutions on the homework if you have to, but try to wean yourself off of them. Then when you go to take the practice test, you'll see them again and you don't use the solutions. The numbers are all different. You can see if you actually learned it or not. Got it? All right, factor that into your study schedule. Get out of here. Thanks for the extra time. Sorry I went over 4 minutes. If you have any questions,